Hello, I'm going to read from my paper. These are two books I have in mind. I want to explain concepts and modeling of a tessellated molecule surface first. This is my first publication, and I did it as a college student. It was published by Robert Lang, published by A.K. Peters and edited by Robert Lang. I can start reading pretty much immediately. I do want to mention one thing here is that where I started with the background, this is essentially a memo. If you pay attention to how I carefully wrote this, you can see that the background section, and there are many, the second being the introduction. The background section is in a memo style, sort of like Star Trek, where the memos read out there in the stars. So I will start reading now. The use of repeating folding patterns has produced polyhedral surfaces with remarkable geometric properties. These surfaces have both flat folded states and three-dimensional folded states and provide solutions to packaging problems where large surfaces must be deployed from small areas. Moreover, folding polyhedral surfaces have a variety of uses. For example, Miura made use of one such surface in his design of maps and atlases. Zhong-Yu made use of another such surface in his design of an expandable heart stent. In fact, such surfaces have also been found operating in nature. In a paper on leaf forms, H. Kobayashi and others discussed how leaves of Carpinus betulus and Fagus sylvaticus deployed similarly to a polyhedral surface called Miura-Ori. So here, this paper will focus on the surface associated with Yu's expandable origami stent. The design of this surface has a history, although there have been several, if not many, independent discoveries of the crease pattern for this surface. The first published appearance of the crease pattern was in 1982 by Fujimoto, who used it to make rigid cylinders. However, this rigidity was not too pronounced. Yu showed that although Fujimoto's cylinder was rigid, it deployed with small deformations and could function as a stent when made with semi-rigid materials. With that said, this type of cylinder rigidity will not be discussed in this paper. While the crease pattern shown in Figure 1 was studied by Yu with the cylindrical connection, this paper will explore the same crease pattern and corresponding polyhedral surface without the cylindrical connection. And I continue now to the introduction. Remember, this is my paper, so it's all things I know. Many polyhedral surfaces using repeating folding patterns work on a common principle. By tessellating origami molecules in a crease pattern, basic origami folds produce complete surfaces. Our goal in this paper is to discuss one of these surfaces called a tessellated waterbomb surface. And then I give a definition. A tessellated waterbomb surface, or tessellated waterbomb for short, is a polyhedral surface consisting of interlocking waterbomb molecules whose crease pattern is arranged as shown in Figure 1. Such tessellated waterbomb surfaces have many folded states, and as they change shape, they morph between these folded states. For example, Figure 2, which is this, shows a basic empirical result. Elongating the highlighted region of a closed model as shown deploys the tessellated waterbomb, giving it a cylindrical shape. As we will show, the highlighted region in Figure 2, called a line of latitude, controls that action. And this darkened part is the latitude. I give another definition. I say a line of latitude, or latitude for short, is a string of waterbomb molecules connected laterally, and that means by side, along axial lines as highlighted in Figure 2. And then this is also completely important. The pertinence of this naming scheme is shown within another experimental tessellated waterbomb in Figure 3. When placed in a circular shape, the many lines of latitude of a tessellated waterbomb appear to shrink and expand with some similarity to the latitudinal lines around the Earth. The body of this paper will be devoted to further discussing the relationship between a latitude and the regions around it. In order to show that a line of latitude controls the action shown in Figure 2, we will assume a line of latitude has been put in a rigid folded state in which all vertex points along that line of latitude, have been fixed in space. Then we will show that fixing these points fixes an entire region called a rigid neighborhood around that latitude. Thus, if a latitude is put into a rigid folded state, then a neighborhood around that latitude must also be rigid. That sentence there is the conclusion of the paper. Here's another picture which shows the unfolded page and then the folded page, and it invokes some justification. Surface analysis. Every crease in a three-dimensional folded structure contains two faces, and together a crease and the two faces it borders make a hinge. By hinge, I mean these things here. A selection of three types of hinges found within these tessellated waterbomb surfaces labeled as R, G, and B are shown in Figure 4, with the exception of a special class of exceptional cases for the B hinge. These three hinges are in a rigid folded state when the position of their base segments, defined by 3 points, are fixed in space. That's the pure math part of this paper. Because of this relationship, we may define functions that output the missing tip of hinges given the input values of 3 specific points for each R, G, and B. These functions called R, G, and B are defined in equations 1 through 3 here. And it's no coincidence that R, G, B are colors, abbreviations of colors, because it's a commonly justified nomenclature scheme. There is now ideas to color the surface of this paper with light. So R, G, and B can also be light. Each of functions R, G, and B respectively operates on 3 domain points on the tessellated water bomb, 1 point on each side of a hinge crease, 1 point on the hinge crease. And that refers to the, dots here. These are the points I refer to. As an aside, for the course of this paper, the explicit definition of functions R, G, and B are less important than the observation that they exist. However, since the explicit definitions of these functions do exist, are not too complicated, and would be useful for calculating the curvature and position of points within rigid neighborhoods in a practical setting, it is worth mentioning that in all but a few cases, vectors Q, M take on varying scalar values. For example, suppose we wanted to calculate the value of M that is associated with our B hinge. We would first define C equal to a C minus B, A equal to an A minus B, to form the base vectors of the hinge. Then let M equal something called a cross product times a vector with an absolute value norm type thing. And then since M has the same magnitude as its base segments and is perpendicular to them, that's a little geometric proof right therein. Thus, for our B hinge, we would have equal to 0 and F equal to A divided by C cross A. This is a multivariable calculus or linear algebra type construction. But this is the implementation right there. All this is the implementation. What is most important is that these hinges and their functions R, G, and B fully tessellate the crease pattern plane in a variety of useful ways. For example, see the tessellation in Figure 5, which will be put to work in Figure 6, and may therefore be used to show, as planned, that rigidity extends from one latitude to a neighborhood of higher and lower lines of latitude. That is very clearly shown in these progressions, these iterative progressions here. This is still essentially the middle of the paper. It goes rigidity neighborhood of a latitude. Suppose a latitude has been given a fixed position in space. Iterative use of functions R, G, and B can extend what is known to be rigid from just that latitude to a neighborhood around it. A snapshot is shown in Figure 6, beginning with a line of latitude. R, G, and B are applied wherever possible so that larger and larger portions of our given tessellated waterbomb surface are fixed in space, stopping only when there are no domain points that R, G, and B can operate on. that is another geometric concept, and it shows that there's a stopping point at the top. Figure 7, rigid neighborhoods of several latitudes, A, B, C, D, E. Definition 4, a latitude of size n is a line of latitude consisting of a string of n waterbomb molecules. This is not as easily well thought out, but it's perfectly legitimate, and it is needed to actually build the implementation, which would be done using a algebraic computer algebra system. The more general result is shown in figures 7a through E. If we highlight latitudes of several different sizes, then find the rigid neighborhoods around them using compositions of R, G, and B, we get figures 7a through E, which show the rigidity neighborhoods around latitudes of size 4, 5, 6, 7, and 10 respectively. So there we have, this is 4, 5, 6, 7, and 10. A rigid neighborhood of a latitude is a region of a tessellated waterbomb surface that is fixed in space whenever a given latitude is fixed in space. Note that these rigid neighborhoods can be shown in 3 space. For example, the rigid neighborhood of a latitude of size 4, shown in figure 7a, corresponds to the region highlighted in figure 8, which its latitude, when its latitude is put in the appropriate shape. Here is the analysis of rigid neighborhoods. Figure 7 shows the rigid neighborhoods of several different sizes of latitudes. This section will provide an informal argument as to why these rigid neighborhoods are the largest rigid neighborhoods fixed in place by their latitudes. The argument relies on 2 considerations: a certain count of creases emanating from the vertex points along the boundaries of rigid neighborhoods, and a previous result discussed by Balcom. And Balcom is another researcher. Here's another definition to prove what I just have stated in the paper. The exterior count of a vertex on the boundary of a rigid neighborhood W is the number of creases emanating from that vertex that are both outside of W and off the boundary of W. This is explained visually where I point to here. An illustration of an exterior count of the many vertex points of W is shown in figure 9, where figure 7a has been redrawn with circles where counts are made. Here, identical to all the other rigid neighborhoods found in figure 7, the exterior count of each vertex on the boundary of W has a value of 2 or greater. So the value of 2 is actually the intersection, there. If you see the number of small lines coming into the black point, that number is 3 here, 2, 2, 3, 2, 2, etc. If the exterior count of each vertex along the boundary of W is 2 or greater, then each counter vertex has at least 4 dihedral angles that are not fixed to any definite value. This implies that the region around W is physically flexible and not rigid, since the mobility of a vertex with M creases is M minus 3. That's a robotics, STEM robotics type result. That result, I hope to post will lead to a citation with Texas A&M University trying to classify all the different types of surfaces. It's very important to understand that this says that the surface is inherently flexible. More flexible, for example, than Miura-Ori, the Miura-Ori manifold. I go on to say, in other words, if the exterior count of vertex points along W were 1, then there would be hinge functions that could extend rigidity. But since the exterior count of each vertex along the boundary of W is respectively 2 or greater, assuming that rigidity must come from somewhere already rigid, each of the neighborhoods in figure 7 is the largest neighborhood fixed by its corresponding latitudes. And that's sort of a completeness proof, if you want to call it that. And here's the final written section: conclusions and future research. The purpose of this research was to investigate a latitude as a means for controlling the shape of a tessellated waterbomb surface. After assuming the latitude was in a fixed folded state, 3 types of hinges and their associated functions were used to find what area around the latitude was also fixed in place. Consequently, we have shown that a latitude does, in fact, control the shape of a tessellated waterbomb surface, though not the entire tessellated waterbomb surface, and we provided some justification as to why this is the case. Our findings suggest a variety of future results. There are 2 that could presumably be shown using the methodology within this paper. First, the correspondence between latitudes and their rigid neighborhoods can be extended to tessellated molecule surfaces with some generality. For example, try a tessellated fish-based surface. Second, the position of points within more general rigid neighborhoods may be defined quantitatively. Thus, the applications of tessellated molecule surfaces may be further studied, and properties such as localized curvature fully defined. That concludes the paper.